Welcome aboard Station 204. This is tomorrow's Space Orbit 12.25. My name is Jamie, and I will be your host for this show. We've also got a Manju, first time hosting with a guest, so that's going to be a lot of fun. We're excited to have you interact with the social chat room and whatnot. And today we've got an exciting guest on, Dr. Rob Hoyt. He's the CEO and Chief Scientist of Tethers Unlimited. He's got a BA in physics from Williams College and a PhD in aeronautics and astronautics from the University of Washington. He's what I like to call a serial space entrepreneur. That's because from 92 to 94, he was at the Los Alamos National Laboratory. Then from 2002 to 07, he was a Science Ops co-founder. And then from 2015 to now, he was the CEO of Off-World Services, which is an offshoot of Tethers Unlimited, where from 1994 until now, he is the CEO and chief scientist. He also, because he just has to add more.
That's enough.
I know, not enough, exactly. Speaks 5 different languages: English, Chinese, German, Latin, and C++, because programming is a language.
Obviously.
Question, I wonder, I'll ask maybe later, which one is the hardest language? I bet it's probably not C++. So getting straight into it, you clearly do a lot in aerospace and inside of industry. What makes aerospace and just space in general important to you?
I think I've always been really passionate about helping mankind become a spacefaring society. I think that started out back when I was a kid reading science fiction, and then was increased when I got to meet Dr. Robert L. Forward, and when I was in grad school, and I started working with him on space tether technologies. And he helped encourage me and a lot of other people in the space industry to pursue some big dreams and take on some really hard challenges and try to figure out paths towards taking things that currently may be in the realm of science fiction, but figuring out ways to make progress on them, make them practical, turn them into products and services that we can make real and get up on orbit. So again, my passion is for helping mankind to become a spacefaring society. That's a long road, but we're chipping away at the problem.
Can you talk to me a little bit about that road? Like it's a long road, you're chipping away at it, but like what are some of those challenges of turning sci-fi into sci-fact?
Well, it's a multi-dimensional problem, because we want to do some really big things, like have people living, working, playing, and growing in space, but there are many technologies that need to be developed to enable that, and there needs to be a good reason to go and ways to support an economy to enable people to live in space. So over the past 20 years, we've been focused on trying to help bootstrap an economy in space. And part of the challenge there is you have to build up the whole supply chain, both the supply side of the equation and the demand side of the equation, in unison, so that people can start up a business getting space resources, and then have customers who are ready to take those space resources and turn them into things of value, and then at the same time have customers who are ready to take those things of value and put them to use. So we're working across a pretty wide spectrum of space technologies, addressing how do we get space resources. Initially we'll launch raw materials from Earth, but that's still expensive. So we'd like to be able to repurpose or recycle materials that we can get in space, such as trash that's aboard the space station or space debris objects, recycle those and turn them into new things of value, such as antennas or structures for habitats. And then, then we need the capability to integrate those new components in space into functional space systems. So we're working on robotics and connectors and other capabilities to enable in-space assembly of things that we make in space with things that we launch from Earth to make new kinds of satellites and stations and exploration spacecraft. And then we need, to have a valid business reason to do that. So we're also working on trying to exploit the unique products that we could make in space, such as very, very, very large antennas or long structures with long baselines for interferometry or other sensing, to take those new kinds of things we can make in space and provide new kinds of services to other businesses and governments operating in space, as well as customers here on the ground.
Go ahead.
One question I'm always really interested in asking founders or co-founders, because Tethers Unlimited is doing, excuse my voice, by the way, Tethers Unlimited is doing a lot of cool work in everything related to the in-space industry, whether it's manufacturing or assembly or what have you. Was there a moment or experience that you had that made you want to found this company?
Well, so I, in some ways, I sort of fell into this. I didn't really go through school thinking I was going to be an entrepreneur or a businessman. I wanted to be a scientist or engineer, and I wanted to work on cool stuff that was going to, change the future of humanity. But I got pretty lucky in that when I was in grad school, Dr. Robert Forward came to the University of Washington, where I was working on my master's, and he gave a talk on space tethers and all the cool things you can do with them. And I had already been interested in space tethers from some of the plasma physics and astrodynamics schooling I'd had in college. Towards the end of his talk, he said something like, well, tethers are great, but unfortunately, none of this will really work because space debris will cut space tethers. And he kind of hinted that he might have some funding in the near future to support a student to help him on a project related to that. And this was when I was supposed to be studying for my qualifying exam and, was looking for any way to procrastinate that. So I went home and messed around on my old Mac Plus and came up with some ideas and ended up sending him a letter with some of my ideas. And then a few days later, he called me up and said, well, I think you already did my project for me. How about you work with me on this project? So at that time, we worked together for a few months. Then I went off to Los Alamos to do my PhD research. And as I was finishing up, we saw that there was a NASA small business solicitation for space tether technologies, and we decided to go after that and submit a proposal to it. And it just so happened that a few days before I was graduating with no job lined up, we won a phase 1 small business contract. So a few days after I graduated, we founded the company and started working on it. And I've never had to get a real job.
What does one use a space tether for?
There are a number of different ways that you can use tethers in space. So a tether is basically a long string or cable deployed from a spacecraft. And you can use them to tie multiple spacecraft together so that they fly together in a formation, so that you can do things like long baseline interferometry or other sensing modalities. If the tether includes a high strength cable component, you can use the tether to transfer orbital energy and momentum from one satellite to another. So if you have like a long rotating tether, you can pick up a payload from a low orbit and fling it up to a higher orbit. And then if the tether has a conducting wire in it, you can flow current along the wire, and that current will interact with the Earth's magnetic field and create what's called a Lorentz force. So the tether is acting kind of like an electric motor. And you can use that to push a satellite around in orbit by reacting against the Earth's mass itself. So you can do propulsion in orbit without having to burn up propellant. So it's very good for things like an orbital shuttle or a satellite that needs to continuously maneuver throughout its lifetime.
So in my notes, I actually had made note that that was a product for deorbiting satellites, but based on what you just described, could you use that for satellite station keeping as well, just to keep it in its proper orbit? Because satellites like to move around a little bit, and we've got to kind of like bump them back to where they need to be.
Yeah, one potential application is doing station keeping. You can do orbit raising or deorbit, and we have a couple products up in space right now that are designed to do that. And one of the more interesting applications is where Tether is particularly good is changing the inclination of a satellite's orbit. Normally, that is extremely expensive because it takes a huge amount of propellant to do that using traditional thrusters or even high efficiency electric propulsion thrusters. But because the tether doesn't need to burn up propellant to provide the thrust, as long as you can wait a few weeks or a few months, you can significantly change the inclination of a satellite's orbit. So you could deploy a satellite from the space station, which is about 51 degrees inclination, and then you could kind of torque the orbit up to be a polar orbit or torque it down towards the equator. So that's a really unique capability that a electrodynamic propulsion tether can provide.
Are you flying these today? Are you going to be flying them soon? What's your timeline look like?
Unfortunately, funding for space tethers has been pretty inconsistent. Roughly every 10 years or so, somebody in the government gets interested in them, and we work on it for a while, and then NASA changes its mind or something like that. So we have flown a tether of our own back in 2007. We currently have 4 of our deorbit tethers on orbit right now, and the first one should deploy or activate roughly a month from now, towards the end of September. But we're still looking for the opportunity to fly a electrodynamic propulsion tether. I should note that there have been over 20 space tether experiments that have flown in the past. And unfortunately, tethers have gotten kind of a bad rap or a reputation for not working. But the truth is that over 70% of those prior space tether experiments have worked perfectly. They've met all of their mission goals. But unfortunately, there were a couple of big high-profile failures when NASA tried to fly what was called the TSS, or Tethered Satellite System experiment on the space shuttle. And there were a few mistakes in the design of that system, or the assembly of that system, that led to failures 2 times. So unfortunately, in the upper echelons of NASA and some other organizations, there's an impression that tethers don't work. So that's something we always have to kind of struggle against. So, but prior experiments have shown that if you do it right, a tether can work, but it is a complex system. It's not just a string that you deploy in space. There's a lot of complexity that goes into getting it to deploy properly and operate properly. But if you do all that right, it can work. So we're still looking for opportunities to fly an electrodynamic tether or momentum exchange tether. And hopefully before I retire, we'll get a chance to do that.
Are you seeing? Go ahead.
No, there's just been a few questions in the chat room about if tethers can be used to reproduce gravity or create artificial gravity, and if you've worked with NASA to reproduce either lunar or Martian gravity with the tethers.
We haven't specifically worked on a project like that, but that is another great application of space tethers. If you connect, say, a Mars transfer capsule with the upper stage that launched it into Mars transfer orbit and get the tether rotating, you can use the centrifugal force to provide artificial gravity to the astronauts who are traveling to Mars. So that is a viable use of tethers. In the near term, a very interesting experiment to do would be to use a rotating tether in Earth orbit or elsewhere to evaluate how much gravity do we need to support astronaut health. Because right now we don't really know. We only have data points at 1G and at 0G. We don't know if you need, a tenth of a G or half a G, or if you need a whole G to fight off the deleterious effects of zero G.
So you had mentioned that there were some failures in tethers in the past, and there's kind of this general NASA mentality of like failure is not an option, and it seems like that's spilled over even into testing, in which failure should absolutely be an option, especially in testing. With new space coming on the scene, we're starting to see these companies testing stuff, having very public failures that they're like, yep, that's part of the testing process. Are you seeing any shift in the industry to maybe allow for some additional testing of tethers with a little bit more leeway towards, it's a test, it might fail, as long as we get data back, it's okay?
I think there is something of a shift there. And the main driver of that has really been the advances in small satellite technologies, where you can put together and fly a meaningful, useful mission for a few $1 million instead of having to spend hundreds of millions of dollars. So, as an example, back in 2007, we did a space tether experiment called MAST. It was intended to deploy a 1 kilometer long tether and inspect that tether over a number of months so we could see how quickly it gets just degraded by orbital debris. The mission was only a partial success or a partial failure. The tether did not fully deploy because we had problems with our separation system. It wasn't really a failure of the tether in my mind. It was a failure of the separation system. But we learned, got some useful information out of it, and got experience operating and flying a small satellite. And that led to a number of follow-on projects. But it was, another failure of space tether technology that kind of that made it a little bit more problematic to push tethers into use. But we're still looking for, still pursuing and have some leads on opportunities to fly tethers in the future. One example is we've been supporting a NASA Goddard-led program that's looking to fly 2 small satellites in a very low lunar orbit and connect them together using a tether. And by doing that, you can get the lower satellite to fly within a few kilometers of the moon's surface for long periods of time. So you can get data on the near lunar surface environment, which you couldn't normally do with a free-flying satellite because lunar orbits are typically fairly unstable. So that's an example where we hope to have a chance to fly a tether within the next few years.
And I know we want to get to some of the other projects, but David on YouTube asked what the system looks like and what causes failure versus not. So I know you had mentioned that in one of the cases it was a partial failure because the tether didn't deploy. What are other ways failure manifests with the tethers?
So as I said, most of the tether experiments that have flown have worked well, but roughly a third of those have run into problems during deployment. And part of the challenge there is you're trying to deploy a flexible tether in a zero-G environment. So you don't have a whole lot of force available to help pull the tether out and stabilize it. There have been of the missions that have run into problems. There have been a couple different ways they run into issues. One of them kind of used, in my opinion, the wrong way of deploying the tether. They had the tether stored up on a spool, and they were feeding the tether out. And in zero-G, that's kind of like pushing on a rope, which doesn't work terribly well, and not terribly surprisingly, they ran into issues. On the shuttle experiment, the first time they tried to deploy the tether, what happened was there was a bolt on the deployer reel that was a little bit too long, and it caused the deployer mechanism to jam, so they couldn't get the whole tether deployed. And when they did a failure analysis, what they figured out that when that bolt was put in, they didn't check that design change against current blueprints, so they missed a clearance problem, and that caused a jam in the system. So that wasn't really a fault of Tether technology. It was a failure of the mission assurance or mission execution process. But again, going back, you've got this challenge of you got to deploy a long, flexible structure in a zero-G environment, and you got to do it correctly with deploying the end mass at the right velocity and controlling the tension in the right way to be able to do that successfully. But again, that has been demonstrated successfully by multiple missions.
And then one more question about the tethers while we're on the subject from Rebel in the chat room. How long does a tether have to be considered stable?
That's kind of the answer to that is a little bit fuzzy. Once you get the two satellites separated by even a few meters, there's what's called a gravity gradient force, where the lower satellite feels a stronger pull by the Earth's gravity than the upper satellite does. So the gravity gradient will tend to pull the satellites apart and tension the tether. If you do it properly with just a few meters of tether deployed, the system can be stable, but the gravity gradient then is really tiny. So if you have any kind of disturbance like solar pressure or other things, that can tend to destabilize it. But multiple tethers of half a kilometer, a few kilometer have been deployed, and they have been stable. So I generally consider it as long as you can get about 100 meters of tether deployed in a reasonably controlled manner, the system can be stable and well behaved.
So we've talked a lot about tethers, but you're doing a whole bunch of other stuff. When we first started talking, you're talking about building an entire space-based economy, and while tethers can serve part of that, certainly looking at actually building things in space. And there are two projects that I'm really interested in. One is building truss structure in space, and two is recyclable 3D printers in space.
Cool.
I know, really cool. Can you talk about those projects a little bit?
Sure. If you want to bring up some of the illustrations I sent you, we could start off with that first slide if you're able to call that up. So overall, our objective is to help create a robust and sustainable in-space economy. But as I indicated, there's a lot to develop there, and a lot of challenges we need to address to enable to get an economy going. And since I tragically am not an internet billionaire, we're having to kind of chip away at that at an incremental and opportunistic manner. So overall, this slide is meant to illustrate our overall strategy. We've started off over the past 10 years developing a handful of high-performance components for small satellites, trying to enable CubeSats and nanosats to do really useful missions. And we've now got those products out of R&D and into production. Those products include a thruster that uses water as propellant. It's called Hydros, and that I'll come back to that later. That's really important to enable an in-space refueling architecture. We've got a line of small software-defined radios called Swift that are now being used in a number of small satellite missions to enable large data transmission capabilities on very small satellite platforms. And then we've got a gimbal mechanism called Cobra that's useful for pointing intersatellite communications links and thrusters and antennas and other kind of payloads. So that part of the business is now, I would argue, in the growth stage, where we're really focusing on ramping up our production to meet the needs of multiple small sat constellation efforts. The second area we're working, and we've been working on that for about 5 or 7 years, is leveraging those small satellite components that we've developed to enable new kinds of satellite services. and in particular, creating small satellites and in-space platforms to provide hosted payload services. One of those is what we call the Hyperbus, which is a small satellite that's really designed to make it very easy for customers to integrate their payloads onto the bus, and make it very easy for them to operate their payloads when they're on orbit. So we kind of refer to it as just being an Ethernet port in space. And then the next market we're working to develop, and we're in the R&D and develop, R&D and maturation stage on those technologies, is creating new kinds of in-space services, such as in-space refueling, in-space assembly, servicing of satellites, and in-space manufacturing. We've got a number of different projects that we're working on there. Some of those are working towards being able to build a microsatellite class robotic servicing vehicle that we call Leo Knight, which could perform many of those jobs of in-space refueling and in-space servicing. Let's see. I can't remember which slide is up next, but if you want to pull up the Refabricateer. Oh, okay, let's talk about this one. So this provides a little bit more detail on some of our small sat components. On the left there is our Hydros thruster. And again, that uses water as propellant. So it's completely safe for personnel during satellite integration, and it's not going to provide a threat to primary payloads, the big satellites that you ride along with during launch. But it's not just a steam rocket. What we're doing is we're splitting the water into hydrogen and oxygen using a process called electrolysis. And then we can burn the hydrogen and oxygen in a traditional thruster nozzle. So this thruster can provide very high thrust and very good fuel economy to enable small satellite missions to do large maneuvers and do station keeping for long durations in orbit. In the center there is an example of our Swift software-defined radios. The software-defined aspect of it enables the frequency and modulation and other operating characteristics to be controlled by software, so we can change how the radio operates while the satellite is flying. So you can use multiple different ground stations as you go around in orbit. You can change the frequency so that you can deal with the very congested, crowded spectrum in space. And we've recently implemented IP-based networking capabilities on the radio, so we can get multiple satellites tied together and sharing data and timing information using simple IP networking protocols. Why don't you go on to the next image? As we're trying to create a in-space economy, there are many different markets that commercial entities and governments are trying to develop, such as developing asteroid resources. There's companies like OrbitFab that are developing propellant depots. There's companies like Made in Space who are doing microgravity material manufacturing, and there's possibilities for space debris recycling, which we're working on. But each of these individual markets by themselves have kind of a chicken and the egg problem, where even if, say, Deep Space Industries or Planetary Resources had been able to go out and get some asteroid resources, they wouldn't have had a real viable business unless there were other businesses who were stood up and ready to take those materials and transform them into things of value and then sell them to other companies in space. So the big challenge that we and everybody else in the new space and traditional space industry have is we've got to bring up the whole supply chain, both the supply side and the demand side, in unison, and get them all started kind of together so that we can have a functioning in-space economy. And we see the off-world manufacturing and services supply chain as kind of the key element that can help tie all these different markets together and make a functioning economy in space. So next slide. So one of the aspects of that is, how do we get materials to enable manufacturing of things of value in space? And initially, we may send raw materials from Earth, such as spools of 3D printer filament, like Made in Space, and we and a few other organizations are doing. But that's still very expensive to launch those raw materials from the Earth. So the next stage in that evolution is taking waste streams in space and recycling, and repurposing those to make new things of value. So we built the Refabricateer payload, working with NASA's in-space manufacturing program. The Refabricateer payload, it's up on the space station right now, and it integrates a plastic recycling system with a 3D printer. So the astronauts can put pieces of plastic waste into a hopper, they get melted down and turned into 3D printer filament, and then we can use that 3D printer filament to make new things that the astronauts may need, such as medical and food safe tools. So that's kind of the next step that we're working on. But as we're developing these in-space recycling and manufacturing technologies, we're also thinking about how can we in the future ingest materials that we can in situ resources, such as materials we can get on the moon or on asteroids. So that's kind of the next step beyond the Refabricator and similar technologies.
When I was at,
do you have a question?
Great.
No, I was just going to say, when I was at interning at NASA, the concept of the Refabricator was something that came up constantly when we were talking about putting humans on Mars, because we can't predict all the tools that we're going to need for living on Mars. And so this concept was something that we were constantly talking about. And you mentioned this is what you're working on next. What is the timeline for the Refabricator right now?
Well, the Refabricator is up on the space station right now. And what we're trying to demonstrate is essentially a capability for closed loop manufacturing and recycling. So the system is designed, it starts out with a block of like a brick of plastic, and it's designed to recycle that brick into 3D printer filaments and then make a number of samples that we can use to test the strength and other properties of the plastic, and then it'll recycle those and make them again and again and again. So what we're trying to do is see how the plastic changes and degrades over multiple recycling and printing cycles, so that in the future we can tell the astronauts, how many times can they reuse the material before it's not going to be either printable or useful for whatever they need it for. But as you mentioned, the objective of this is to create a capability to support long-duration manned missions, such as a mission to Mars, where if we had to send them with all of the replacement parts, all of the medical devices, all of the spoons or whatever that they would need for a 2 or 3 year mission, that would require a huge amount of launch capability, multiple launches, and cost many hundreds of billions of dollars. But if we have a Refabricator capability, we can send them with a limited amount of feedstock material, and then as things break or as they need a new tool to do, a science mission or whatever it is they need to do, as it comes up, they can just make those tools, use them, and then recycle them into what they need further down the line.
So the tools make sense because you could pretty easily make that out of a rigid plastic in many cases. But a lot of the components on space station or spacecraft will be made of metal. So are you looking at any form of metal sintering in space? Or is that like really far down the road and just a completely different technology?
That's another area that we are supporting right now. It's kind of the next step beyond Refabricator is to create the capability to do precision manufacturing of mission critical parts. So NASA's in-space manufacturing program is funding Tethers Unlimited and 2 other small companies to work with them on a program called Fab Lab. And the objective there is to put together a integrated system that can do automated manufacturing of precision metallic parts. So the 2 other companies are developing 3D printing, metal 3D printing based technologies. And our part of the effort is we're working to integrate robotics for manipulating parts and inline inspection capabilities so that we can monitor the manufacturing processes and make sure that the part comes out with the right dimensions and the right properties. That's in a phase A program right now. That'll be ending early next year, and hopefully some or all of us will get to move on to the phase B, working towards a system that can fly.
It seems like it's a pretty difficult challenge too, right? I mean, when you think about metal sintering, you've got like, I assume it's that same concept. You've got like a powder. For those who don't know, you've got like a powder of metal, titanium, aluminum, Inconel, whatever you want, and you shoot it with a laser, and it kind of like bonds to the layer underneath it. And in one gravity here on Earth, that's not a big deal because it just kind of all sticks down to everything. But when you start going into space, you've got microgravity. How do you hold that powder down? And then you've got an outgassing problem. So like where does all of that go? These are actually pretty challenging things to solve unless you're taking a completely different approach.
Yeah, the Fab Lab program is taking a different approach. The 2 companies that are doing metal 3D printing are not using powder-based approaches. My understanding is they're using kind of wire feed type approaches, in part because having a powdered substance in 0G on the space station would likely be a very significant health and hazardous threat to astronaut safety. Here on the Earth, there have been examples of powder-based metal 3D printing systems blowing up. So that would be a big no-no on the space station. So the Fab Lab project is focusing on things like wire feed 3D printing that can be implemented in a much more safe manner. We, under a NASA small business project, are working on essentially 0G milling of metals. So what we're doing is we're doing recycling of metallic pieces to make a puck or a billet, and then doing kind of traditional milling of it to make a part. But the challenge there is the milling process creates a lot of little chips, and we have to make absolutely sure that none of those chips can escape from the machine and get into the astronaut's habitable volume. So we're working on ways of ensuring that we collect all those chips and then are able to recycle the chips to make new billets. That's a project that's called Mamba.
I'd say the thing that I don't think a lot of people realize is that in microgravity, when something flies into your eye, how do you get it back out? So if you've got a little metal shaving that gets stuck in your eye, you can't just flush your eye with water. That's not going to be a thing. So keeping all of that contained would be extremely important, it sounds like. Yeah, absolutely.
Yeah, on the Refabricateer and Fab Lab, we've learned quite a lot about the requirements for ensuring astronaut safety. The process is quite rigorous. There's a lot of testing, a lot of paperwork involved, but it is critical because the astronauts don't have a urgent care that they can go just run down the street to go to. We have to make very sure that these systems and experiments don't pose any kind of hazard to the astronaut safety.
I think we also have a couple of different videos that Dada's got queued up. First, Dada, and I do get to say it, and I'm going to take this moment away from you. I'm sorry. But Dada, could you release the Kraken for me? You have to say it with more energy, though. Release the Kraken! What are we looking at here?
Okay, so the Kraken is a compact robotic arm that we've been developing to enable in-space services, in-space assembly, and other applications. And the past couple of years, we've been working under a NASA small business contract to develop a payload for the space station called Mantis. that will have one or two of these robotic arms, and it's intended to enable remote operation of experiments on the space station, so that we can kind of offload menial and repetitive jobs from the astronauts who are very busy, and get underpaid grad students on the ground to do our science on the space station. So the Kraken is designed to stow into a very small volume, as you see there, but we've also done quite a lot of work on it to ensure that it's safe to operate around astronauts. Now, there are in terrestrial robotics, there are what are called co-working robots. But those systems, if they run into a human or other obstruction, they just stop and lock up, which isn't acceptable on the space station, because you can't have the arm being an obstruction to astronauts if they need to get to an escape pod or something for an emergency. And you need to make sure that if the arm is doing something and an astronaut drifts into the way of the arm's not going to hurt the astronaut. So the Kraken integrates very precise force and torque sensing and new capabilities for precisely controlling the amount of force and torque that the arm can apply. So as you saw there in the video, we can, if the arm is, say, moving a payload around in zero G, we can calculate exactly how much force it needs to be able to do that, and tell it to apply only that much force, so that if an astronaut needs to get the arm out of the way, the astronaut can just push it out of the way, and an arm will flop out of the way until the astronaut's moved on to other things, and then the arm can come back to doing what it needs to do. So it's been designed to enable it to operate around astronauts and be safe. For future applications where we'd like to use the arm on the outside of satellites to enable things like capture of space debris and satellite servicing and assembly, those force and torque sensing and control capabilities will also be very useful. For example, if you want to capture a piece of space debris, that space debris is likely tumbling, and you don't want to just grab it instantaneously and have the tumbling satellite rip the arm off your satellite. We can, with the Kraken arm, we can grab onto the target object and very precisely control how much force we apply to it, so we can bring it to a gradual, graceful halt, and then deorbit it or recycle it or whatever we want to do with it.
And I think we had one more video as well. It was the Truss video, is that correct, Dada?
Trusselator, yeah. So we've been working for a number of years on capabilities for in-space manufacturing of composite structures. So this is a time-lapse video of an early prototype of the Trusselator manufacturing a 10-meter long truss out behind our laboratory. The system takes spools of carbon fiber composite, which can be packaged in a very compact manner, and uses processes similar to 3D printing and similar to composite layup to transform those spools of carbon fiber composite into trusses that are extremely lightweight but extremely stiff. So you can see this example is supporting itself in 1G. It's 10 meters long. It's actually stiff enough that you can swing it around like a giant lightsaber. And because our engineers are engineers, of course, they did that.
Wait, why don't we have video of that? I want to see that. That sounds amazing.
They didn't do it where I could see it.
Smart engineers. They're smart engineers, absolutely. You had talked earlier about kind of a satellite platform, and it sounds like you've got an Ethernet port in space, and I think that's a really good way to describe it. It sounds like you've got everything necessary where if I wanted to fly something like a camera in space and I want to get a really beautiful shot of Earth, you've got most of the tools necessary for the satellite platform itself, including the on-orbit station keeping. You have got the communications, the space-to-ground communications itself. Sounds like you've got potentially a bit of the avionics, if I kind of understood that a little bit, or at least the control mechanisms there. And then I just plug into that Ethernet port, and I can start beaming down whatever I need from space. And just in case I need a robot, you've also got a Kraken that allows me to then like interact with other things. Well, I mean, who doesn't want a robot on the satellite, right? I feel like I just need to have the robot on the satellite. And then also this Truss. So how does all of this fit together? Are you looking to like, you've got these small platforms that, you know, people like me, I could get a camera and put it together, but then you've also got the Truss. Are you looking to kind of like use these pieces together to build bigger things in space?
You're catching on. So we have a number of the components that you need to build a satellite. Right now, we provide those to a number of big and small satellite integrators for their satellite systems. But what we're working towards is being able to build platforms that will stay on orbit, and we can build them up in a modular, incremental manner, and then they can host multiple payloads, and so that customers, whether in the government or commercial, only if they want to get a sensor on orbit or a transponder or some other payload, they don't have to go buy or build a whole satellite bus. They can build just their payload and launch just their payload, and then we can plug it into a platform on orbit and provide it all the services it needs, the gas, light, power, and cable, and get them operating much more rapidly and with significantly lower initial investment than the traditional route where they'd have to go and buy or build a whole satellite. So yeah, what we're working towards is being able to build what are called persistent platforms or orbital outposts that we can build them up incrementally, so we can start small and add more modules, more capabilities over time, and upgrade and increase the capability of the system over time.
What additional breakthroughs are necessary for you to be able to realize this vision?
Well, there's still a number of technologies and capabilities required. One of them is connectors to enable modular space systems to be assembled together by robots in space. We're working on a couple such connectors. One is called the Axon connector, but there are also a number of other small and big companies who are working on different kinds of connectors. Some for in-space refueling, some for assembly and robotic servicing of vehicles. Certainly, I hope that our Axon connector will be used, but there are a lot of good minds in the industry working on this, and we're eager to work with whoever has the best solution. There's also advances needed in autonomy to control the robots, as well as teleoperation capabilities, so people on the ground can control the robotic systems. One of the challenges you have to deal with there is communications latency and communications dropout, where there's a significant lag in between when a operator on the ground sends a command and when the robot receives it, and when video or other data gets back to the operator to tell them whether the operation worked properly or if there's any problems. So we're working with another Seattle area company called Olis Robotics, and they have some really interesting technology for teleoperation where they can enable kind of variable levels of autonomy to assist a operator controlling a remote robot. There's also one of the other challenges is if you've got a small satellite that's got one or two robotic arms on them, and it's trying to manipulate a larger object, the dynamics of that are complicated and interesting in that as the client satellite or client object gets bigger and bigger, it's less about your robot manipulating that system and more like your robot crawling around on that system. So we're working on developing the dynamics and control methods to enable multiple robotic arms and multiple small robotic satellites to manipulate bigger systems, so we can do in-space assembly and servicing of large space systems. Another interesting technology that we and others are working on is collaborative robotics capabilities. So, for example, we just got started on a phase 2 small business contract with NASA to develop what we call the Astroporter capability, and that's a capability for robotic systems like our Kraken robotic arm to interact with free flyer robots and other systems, such as the Astrobee free flyer that NASA has put up on the space station. This is like a little cube system that can fly around inside the space station and observe things and help out the astronauts. And what we'd like to develop is a capability for Astroporter or the Astrobee to go and say grab a payload and bring it over to the Kraken arm. The Kraken arm can grab it off the Astrobee and plug it in somewhere and do those kind of operations. But even though that sounds simple, we need to have those robotic systems communicating together as they do that, so that say when the robotic arm touches the Astrobee's attitude control system doesn't freak out and go spinning off and bump into something. So part of what we're developing is what I've been calling kind of a robotic consent protocol. So the robotic system can say, hey, I'm gonna touch you, I'm gonna grab something off of you. Is that okay? Are you ready for that? And we can get these multiple robots working together in a collaborative and successful manner.
Nothing in space is simple. I think that's the takeaway from that.
Right.
Nothing in space is simple. Since the 1950s and even earlier, we've seen these incredible visions of the future where space-based manufacturing was a thing, right? Like these incredible paintings. And up until now, it really hasn't been a big thing, right? ISS, we assembled on orbit, but fundamentally it was manufactured here on Earth and then lofted to orbit and then kind of slammed together. Do you believe that we will have full-on actual space-based manufacturing in our lifetime?
Oh, yeah. We are working on multiple projects to enable in-space assembly and in-space manufacturing. We've got a project funded by DARPA that's called Orb Weaver, where we're developing the capability to take what's essentially a piece of space debris. It's called an ESPA ring. It's a big aluminum ring that goes in between a rocket and the satellite that the rocket is launching. And normally that ring becomes a piece of space debris that you have to get rid of. But that's 170 kilograms of very valuable mass that's on orbit. So the Orb Weaver is a payload that will ride along on that ring, and after it's completed its job, the Orb Weaver will use robotic systems and tools to actually chew up most of that ring and take the little shards of metal that it's chewing up and recycle them and transform that metal into segments for a large antenna reflector, and then use the robotic systems to put those segments together to make a very large antenna. So that's an example where we're hoping to take a piece of space debris and transform it into something of value that we can use for satellite communications or sensing or other applications. And our hope is that by demonstrating that capability, we can tackle this space debris challenge, which right now is kind of an untractable problem, because even though the space debris population is growing and growing and posing a bigger and bigger threat to continued human and robotic operations in low Earth orbit, nobody wants to have to pay to clean it up. So nothing's really being done about it right now. But our hope is that by showing that you can collect a piece of space debris and repurpose it into something of value, we could create a commercial enterprise that would go and clean up the space debris environment on its own nickel, but then make a profit doing that. So that's something we hope to fly, within 4 to 5 years. Another effort, Made in Space, just got a large contract from NASA to demonstrate a capability for assembling a big truss to support a large solar array. And I think that's intended to fly in 2022 or 2023. And then, we and a couple other companies are working on the Fab Lab project, and if all goes well, we should have that up on the space station in, say, the 2023 or 2024 timeframe. So, these are still incremental steps. We're taking baby steps at this point, but I think we are, once we get some of these demonstrated and show the cost and performance advantages that in-space manufacturing and in-space assembly can provide, I think it's going to radically transform the way the whole industry does space missions. And that then hopefully will progress towards building, huge habitats to support people living and playing and working in space.
I don't suppose you ever watched the sci-fi series Stargate by chance, did you?
Did not watch Stargate. No.
Your description of like taking the ring and then turning it into something new sounded like one of the sci-fi tropes they had there, which they called the replicators, which I thought was absolutely hilarious. So a lot of the community who watches Stargate right now is probably laughing. All right. On that note, actually, a great question from the chat room from Sarge Enzyme, which is asking, are you hiring?
We are. We're looking for a good variety of different engineers, space systems engineers, avionics engineers, software engineers, mechanical engineers. We've just gotten started on a pretty big flight experiment to do a demonstration of in-space manufacture of a large structure. That's a project funded by NASA, and we're working with Space Systems Loral on it, and it's intended to fly on the Restore L mission. So we're staffing up to support that, as well as we're on Monday we're getting started on I think 5 new NASA SBIR and STTR contracts, developing things like a tool changing interface for a robotic arm, and a system called Spider, which will enable exploration of craters and other features on the Moon and Mars. And we've got a couple other space flight missions that we've been told we've been selected to do. They haven't gotten started yet, but we're expecting to start on those within the next few months. So yes, we're hiring. If you're a good engineer and like working on really cool, crazy, challenging stuff, please let us know.
I think all engineers like working on cool, crazy, challenging stuff. I think that's like, it goes into engineering blood. If someone wants to find out more information on like what you guys are working on, any of your news or upcoming projects, where can they go?
Well, we've got a website, www.tethers.com. Although I have to admit, I still am our webmaster. And I've been pretty busy, so I haven't updated it in quite a while. Our Facebook page, Tethers Unlimited, is probably the best place to go. We update that with news and videos of things we're doing. So I would say check out our Facebook page first.
Dr. Rob, this has been a fantastic interview. You are working on so much stuff in space. What I think is really inspiring and awesome is that you're helping to build that space-based economy where it's not just everything down here on Earth that's just lofted up into space, but actually building it so that we have an economy in space itself, utilizing the resources of space, which if we're to explore other planets and truly get out of just the little habitation of Earth, it will be absolutely required. And like you said, you're not in the billionaires club, you're just doing what you can to make it happen. And I think that's very inspiring and very awesome.
Okay. Yeah, we need that in-space economy to help justify and support people living, working, and playing in space. And so that's what we're working towards.
Completely agree. Thank you so much for taking your time this Saturday. Hopefully you won't be a stranger to the show. We'd love to bring you on and talk about all the future and amazing things that you bring on. And I do also want to thank.
Thanks very much.
Yeah.
Thanks for your patience with my network issues.
Well, you got to fix that. You got to run a constellation for us, kind of like Starlink, so we can actually get like really great bandwidth no matter where we are. That we've had like space-based cameras for the show. That'd be amazing. I do want to thank all of the patrons of tomorrow and citizens of tomorrow who have helped make this specific episode happen. These are the people who contribute financially to the show. Without you, we wouldn't be able to keep the lights on. We wouldn't be able to keep doing this show week after week. We don't just do our live interview shows. We also have our space news shows. We've got our STEAM shows. We've got a lot of really great content, hopefully designed to get you inspired and engaged in space. If you'd like to figure out how you can help crowdfund the shows of tomorrow, head on over to youtube.com/TMRO/join. And that will also, of course, if you subscribe to the level it's appropriate, we'll also get your name in the show. Thank you to every single name that just flashed up on the screen, because without your help, we wouldn't be able to do this. It really means quite a bit to me. All right, did you have fun?
Yeah, I had a lot of fun. I'm really glad we ended up making it work.
Yeah, absolutely. That was a fantastic interview. I'd like to thank everyone so much for watching, and we'll see you next week.